Hello everyone. In this video, we are going to discuss the principle of heat engine and we will calculate its efficiency. First of all, consider a cyclic process as shown in diagram in PV diagram. A gas goes from state A to state B and then B to C and then C to D and D to A. We form a cyclic process in which the process uh, to isothermal process and to isochoric process. A to B is isobaric process and then B to C is isochoric. Then C to D is also a isobaric process, but D to A is also a isochoric process. First of all, we have to know 2 points in the expansion. First of all, we discuss the expansion. Expansion cause cooling effect, and the compression cause heating effect. As we can see from the diagram, A to B is an isobaric expansion. We consider A to B. The A to B is an isobaric expansion. And we know that the expansion causes cooling. And due to this cooling effect, the heat from surrounding can flow into the system. And let's say it is a Q1 heat which is entering to the system due to its expansion, and isobaric expansion causes the cooling effect. Here the cooling effect, and due to the cooling effect, heat can enter to the system because the external temperature is higher, and inside the gas, inside the container, the temperature is lower due to the expansion. The heat Q1 can enter to the system, and if we move the system from B point to C point, where it is a isochoric process in which the gas lowers its pressure, the pressure goes down B to C. As we see in diagram, the pressure goes down from B to C. The volume remains constant. It is not expansion nor compression, but due to the lowering the pressure, the volume remains constant. According to the ideal gas equation, PV is equal to nRT, and we see that the nr is a constant and volume is also the constant in this process B to C. Because it is an isochoric process, then we can say that our this relation, the pressure is directly proportional to temperature. As we lower the pressure, the temperature will also lower. That means it is also a cooling effect, and due to this cooling effect, it is also a cooling effect. And due to this cooling effect, heat can enter to the system, and let's say this time the Q2 heat can enter to the system. Now consider third process, which is C to D, and C to D, we can say that the C to D is a isobaric process because the pressure remains constant. Let's say it's a pressure P1 and this is a pressure P2, and here the volume V1 and here the volume V2. We can say the C to D, the pressure remains constant, which is the P1, and due to this compression, because the volume decreases from V2 to V1, V2 is greater than V1, then it is a compression, which is called isobaric expansion. Isobaric expansion. And due to this expansion, because we know that the expansion causes cooling effect, and this is also a cooling effect. Sorry, this is a isobaric compression, and due to the compression there is a heating effect, and due to the heating effect the heat can flow out of the system, which we can say that it is a Q3 heat which is going out of the system because a compression causes the heating effect. Now we consider from D to A. Now D to A is a isochoric process in which the volume remains constant and the volume is just V1 at D, and the volume is also the V1 at point A. It is an isochoric process, and isochoric process, the pressure increases according to our ideal gas equation. The PV is equal to nRT, and volume is constant, and this is constant. RT is also the constant. If we lower the pressure is directly proportional to temperature, and if we increase the pressure, here we increase the pressure and the temperature will also increase. It is also a heating effect, and due to this heating effect, the temperature rises in the system. The heat can flow out of the system, which is Q4 heat, and we complete our cycle. We move the gas, go through A to B, and then B to C, and then C to D, and then D to A in a cyclic process. And cyclic process forms, there is a area in this figure, PV diagram. The area in this PV diagram represents to the work done, which is positive number, because the work done in a clockwise direction is a positive, and this positive work done means the work done by the system. By the system means the work done on the system and work done by the system. The total work done is positive. The work is can be done by the system. Net work done is by the system. As the A to B is work done is positive, but C to D the work done is negative because the volume is decreasing. And if the volume is decreasing, the work done will be the negative. The C to D is the work done is negative, but A to B is the work done is positive, because this is the greater positive number and this is the smaller negative number, and we add all the terms, we get the positive answer in a clockwise direction. In a cyclic process, the net work is done by the system in this process, and we consider the two times the heat enters to the system and two times heat leave from the system. The total heat entering to the system can be written as the QH. Total heat entering to the system is Q1 plus Q2, and total heat leaving from the system can be written as the QL, which is equal to Q3 plus Q4. According to the first law of thermodynamics, tells us that the delta Q heat is equal to the change in internal energy plus work done. As it is a cyclic process, the work done in a cyclic process, the change in internal energy in a cyclic process is equal to 0. Then our first law of thermodynamics says that the delta Q, all the heat absorbed in the system, is equal to the work done. And we can say that the delta Q here from these equation 1 and equation 2, we can say that the total heat absorbed in a system will be equal to the QH minus QL is equal to work done. Now we calculate the efficiency of this heat engine. The efficiency can be written, the efficiency will be equal to output divided by input. The output is a useful work done which we get from the system, and then efficiency is equal to the output is work done, and the input is the QH which we provide to the system, the total heat provided to the system, QH. Then the work done, we know that from this equation the work done is equal to QH minus QL divided by QH, and from this equation we can get the efficiency is equal to 1 minus QL divided by QH. All this diagram like this, if we have a high temperature reservoir and if we have a low temperature reservoir, and we can see that the heat is traveling, Q1 and Q2 heat is added to the system, our heat engine, the Q1 plus Q2, which is we call the QH. The QH heat added to the system, here our heat engine, this is heat engine, and here due to this entering the heat into the system, work is done by the system, which is a positive work done in outward direction, and Q3 and Q4 heat leaves from the system. As we can see this diagram, the Q1 and Q2 heat is entering to the system, and Q3 and Q4 heat is leaving out of the system. This to the low temperature reservoir, the Q3 plus Q4 heat is leaving from the system, which we call the QL, and the useful work is done by this system, and this QH and QL, and this diagram, from this diagram we can write the efficiency is equal to the work done divided by input, and input is just QH, and we will left with this relation from this diagram too. Thank you for watching.